In section 11.2, we're going to talk about a model for gases, kinetic molecular theory. This helps us to understand the behavior. What we were just talking about a straw, you could only get a column of a liquid to go up, 10.3 meters. That's an observation. Talking about the atmosphere pushing down and this opposing that, that's more of an explanation, more of a theory. And we have a theory specifically for understanding gas behavior called kinetic molecular theory. Kinetic refers to motion, molecular refers to molecules. And so we're talking about the motion of molecules in this theory. The model is great. It predicts behavior for gases under many conditions, but not all. The nice thing about an introductory chemistry class is we're just going to talk about the situations where it does work, and we'll ignore the rest of it. So these are the ideas in the kinetic molecular theory. A gas is a collection of particles in constant motion. Okay, so, we've been talking about atoms and molecules, and so, that's maybe not so strange. But as humans developed and investigated the world and tried to figure out what air was, is it obvious that the air in this room is particles? Obviously there's something here because we can cause a breeze, like from that stupid fan up there, and we're breathing oxygen, and we know that if there's no oxygen, we would die, but you can't see the particles. And so this was kind of a revolutionary idea. But a gas is a collection of particles, and those particles are in constant motion. They're actually going to just move in straight lines until they run into something. So a body in motion will continue in motion until it hits something. So we can think of them a little bit like billiard balls or like that ancient video game Pong. Have you guys at least heard of Pong? There's this little blip on the screen and you had this line at the bottom and you had to catch it and bounce it back up and it just bounced around. That's what the gas molecules are doing. They go in a straight line till they either run into a wall or the side of a container, or they run into your ear, or they hit another gas molecule, and then they bounce off. The second idea, there are no attractions or repulsions between these particles. The collisions are like billiard ball collisions. We say they're elastic. There's no loss of energy because of the collision. Now, with modern cars, when a car hits something, it's got a crumple zone in the front that absorbs a lot of that energy, and so the car just, and it just stops. It doesn't bounce off. But if you hit a billiard ball with another billiard ball, they bounce off of each other, don't they? And they stay in motion. That's an elastic collision. So they bounce off and they just keep going. Another idea is there's a lot of space between these particles compared to the size of the particles themselves. So a gas is mostly empty space. In fact, the particles are so small relative to the volume that they occupy that we can generally just ignore the volume occupied by the particles. And the last idea is the speed of the particles is related to the temperature. So if the temperature is warmer, then the particles move faster. If the temperature is lower and slower. There's a good way to remember. If the temperature is lower, the particles are moving slower. Another way to think of it is think of barefoot people at Reedley Beach in the summer. Okay, when the sand is dry and blazing hot and you're walking barefoot, you're not going to stroll along on the sand unless you have absolutely no feeling in the soles of your feet. It hurts. It's really hot. So you're going to go really, really fast to get to the water. You go to Pismo, and it's cold and foggy, and that's why we go there. And you're walking along on the sand, and the sand is nice and cool. You just stroll along. Cool temperatures, moving slowly. Hot temperatures, moving fast. Kinetic molecular theory is consistent with the properties of gases that we learned about earlier in the semester. Gases are compressible. They assume the shape and volume of their containers, and they have low densities in comparison to liquids and solids. So we'll look at each of these. So gases are compressible. Here's an illustration of a gas in a container, and this is like a piston or a syringe, where we can take this piston here and push it down. We can change the volume of this container without letting anything out. So with a gas, you can compress it, make the volume smaller, and the particles are still here. All that's happened is they're closer together. We squeeze them together, and we can do that because between these particles is absolutely nothing. It's a little hard to think about because we look at that picture and somehow, at least I mentally think that there's air in there, right? And air can be compressed, but only so far. And you think, oh, well, what about the air between the particles? No, this is looking at the particles themselves, and there's absolutely nothing between them. So you can compress a gas. In liquids and solids, the particles, the molecules, are already touchingly close. They're already very close together. And so if you put pressure on this liquid, you can push on it all day, it's not going to get any smaller. And that's the basis for hydraulic systems and like the brakes in your car. So you have brake fluid in your car, and when you put your foot on the gas, not the gas, oh, it's going to be one of those days. When you put your foot on the brake pedal, it presses on the brake fluid, and that pressure gets transferred through the brake line to the brakes on your tire, and instead of the liquid compressing, it just shifts the pressure, and then it pushes on the brakes and causes your car to slow down. If you have air in your brake lines, then your brakes kind of feel spongy, and you push on the brake, and you have to push a while before anything starts to happen. Because if you have pockets of air in here, the air is a gas and the air is compressible. And so the air will compress, and then when it's compressed as far as it'll go, then it'll shift and work like it's supposed to do. So some of you know a little bit about brakes, and so maybe that was interesting to you. But liquids can't be compressed, gases can. Gases assume the shape of their container. This is not true of liquids and solids. Solids just take their shape, they have their shape and they keep it, and they have their volume and they keep it. And liquids will assume the shape of the container but not the volume. Gases will assume the volume and the shape. So here we have these gas particles in what looks kind of like a mason jar. So if we started out with them all squished down here in the corner, kinetic molecular theory says that gas particles are in motion. And so they move, and this guy moves, and he's going to keep going until he hits something, and then he's going to bounce back. Because they're moving like that, and they're not attracted to each other, they're just going to keep going until they hit the wall, and then they'll bounce back. So like if we think of this room as a container, and we take a little tiny bit of gas, and we release it over there in the corner. Well, what are those particles going to do? Are they going to huddle together because they like each other? No, they have no attraction for each other. Water is different. There's attractions between the particles in all liquids. There's attraction between the particles, and that's what holds them together in the bottom of the container. But those little gas particles over there are moving, and so as soon as you release them, they're not hitting the walls of that little container, so they're just going to go. And so there might be one that comes up here, and he just keeps going until he hits up there. And so in not a very long time, because of that random constant motion, they're going to spread out and completely fill their container. And that's very different than what solids and liquids do. Low densities. There's a lot of empty space. It's kind of hard to understand. If we took one can, and the author must really like orange soda because this is orange soda too. If you took one can of orange soda, took those molecules which are as a liquid, and converted them to a gas, just at regular conditions, they would fill 1,700 cans of soda. That's not a picture of 1,700 cans. Just think about that for a minute. One can of soda, if I make that into a gas, it'll fill 1,700 cans. That's a lot. the gas is 1,700 times less dense than the liquid. Okay, so it's a really big difference.